Okay, let's see. Test 12. Okay. Test number 1. Is the following situation impossible? Is the following situation impossible? A softball pitcher has a strange technique. He begins with her hand at rest at the highest point she can reach and then quickly rotates her arm backward so that the ball moves through a half-circle path. She releases the ball when her hand reaches the bottom of the path. The pitcher maintains a component of a force on the 0.18 kg ball of a constant magnitude 12 Newton in the direction of motion around the complete path. As the ball arrives at the bottom of the path, it leaves her hand with a speed of 25 meters per second. Okay. To answer this question, whether this situation is possible or not, let's see what we don't know in this situation. The question says that the pitcher swing the ball backward in the half circle. If we let the radius of the half circle as r, this is a parameter that we don't know. So let's see that if what is the value of r. We will try to calculate r, and let's see from the results that this value of r is possible or not. Okay, we can use the work energy theorem. We state that the total work done on the ball is equal to the change of its kinetic energy. Work done on the ball has two parts. The work done from the force that the pitcher exerts on the ball and the gravitational work. Since the force from the pitcher on the ball is a constant and point along the direction of the ball, so we can calculate the force by simply multiply the magnitude of the force and the distance, the total distance of the ball from the top to the bottom of the half circle path. Okay, so it is F times pi r. The work done by the gravity, we can calculate this value in several ways. The easiest way is that we know that for the gravity, the work done by the gravity is equal to the minus of the change of the gravitational potential. So when the ball moves from the top to the bottom, if we use the bottom position as a reference, so we know that the gravitational potential reduced with the amount of mgh. In this case, h is 2r, right? We can see that the ball go from this position to the position and the height is 2r. So we have that delta ug here is the minus of mg2r. Work done by the gravity is the minus of that value, so the work done by the gravity is the mg times 2r. Okay, so we have the total work done on the ball is equal to the change of the kinetic energy. The ball starts from rest and then move with the velocity v at the final position. So we have that the change of the kinetic energy is half of mv squared minus 0. Rearrange this equation, we can get r as this term, and we substitute the numerical value. we get R equal to 1.36 meter. So it is quite impossible for a person to have the arm with the length of 1.36 meter. So we can say that this situation is impossible, okay? Because this arm length is not possible. How can we, the normal people have this length, have an arm with this length, okay? So that is for the question number 1. Question number 2. 3 identical balls are thrown from the top of a building, all with the same initial speed. The first is thrown horizontally, the second at same angle at some angle both horizontal, and the third at some angle below the horizontal. Neglecting air resistance, rank the speed of the ball at the instant each hit the ground. Okay, you throw 3 balls like this. The first one you throw horizontally, the second one you throw with some angle with horizontal, and the third one you throw with some angle below horizontal. And you want to determine the speed of the ball when it hit the ground. Okay, we can calculate this quite simple using the conservation of energy. That is, the sum of the chain of the kinetic energy and the potential energy is 0, or we can say that the kinetic energy plus potential energy is always constant because their change is equal to 0. Right? Now, if we use the initial velocity as Vi, the final velocity at Vf, and the mass of the ball is m. They say that these three balls are identical, so the mass of them are equal, right? And the change of the gravitational potential, if we use the reference, if we use the ground as a reference, so the gravitational potential at the ground is 0. The change of the gravitational potential is equal to the gravitational potential at the ground minus the initial gravitational potential, which is equal to mgh, right? So if we add these two terms, it must equal to 0. Rearrange this equation, we have Vf is equal to the square root of this term. And you can see that since these 3 balls have the same initial velocity and are identical, it means that they all have the same mass. So it means that they will all have the same final speed. Okay, so the answer is they will have the same speed. Be careful on this that we talk about the speed, so they all have the same speed, but if we talk about the final velocity, they can have the different final velocity because we have to consider the direction of the ball when it hit the ground, so it can be different. Okay, but in this case we talk about the speed, and from the conservation of energy, they all have the same final speed. Okay. The question number 3. The launching mechanism of a pop gun consists of a trigger released spring. The spring is compressed to a position YA. Okay, you have a spring here. You compress the spring to the position YA. You can see that YA is negative. Okay, and the trigger is fire, so you release the object, and the object moves vertically. The projectile of mass m lies vertically to a position YB. So this is a YB, the maximum height of the object above the equilibrium position of the spring. So if we use this equilibrium position as a reference, okay, the YB will be the distance above this equilibrium position, indicated as position y equal to 0. Okay, so this is y equal to 0. Consider firing of the gun for which M is equal to the 35 gram, YA is minus 0.1 meter or minus 12 centimeter. As I mentioned, we will have the negative value of YA, and YB is equal to 20 meters, which means the spring constant. We can solve this problem using the conservation of energy. Okay. First, we will use the reference point here. This is the equilibrium position of the spring. So at the reference point, we have the 0 elastic potential. Elastic potential of the spring is 0 at this point. And also, we can choose this as a reference point for the gravity, the gravitational potential also. So we have the UG is equal to 0 here, and also US, the elastic potential of the spring is 0 also. Okay. We can now, since both the gravity and the restoring force of the spring are the conservative force, so we can use the conservation of energy. Delta U plus delta K is equal to 0. In this case, it's quite simple because we know that the initial velocity is 0, which means that the potential energy here is 0. And also, the final velocity is 0 because this is the maximum height of the object. So the final kinetic energy is 0. Okay. So the conservation of energy here reduced to that the delta U is 0 because delta K is 0. The kinetic energy at the initial position and final position are both 0. So we have delta K is 0. Now, what is the delta U? The final gravitational potential is mgyb because we use the reference point here, and this, the height here is yb, and the initial potential energy is the summation of the gravitational potential and the elastic potential. Okay, please notice that at this point the object experience the force from the spring, so we have to consider the elastic potential also. But at the final point, there is only the gravitational force on the object, so we have only the gravitational potential at the final point. Okay, and we put this together, and be careful that YA must be negative here. Okay. And then we rearrange to get the expression for K. So we have the expression for K like this, and we put the numerical value to all parameter. And please notice that here YA is negative, so this change to be the positive side here. And then we calculate the numeric the result, which gives K equal to 958 Newton per meter, and we have the solution here. Okay, that is for the question 3. Question number 4. A car traveling at an initial speed v slide a distance d to a halt. It means stop after its brakes. its brakes lock. If the car's initial speed is in state or increased to 2v, at the moment the brakes lock, estimate the distance is slides. Again, we can use the work energy theorem. In this case, we have that the work done by the friction, because the car slides and there is a friction between the load and the car and the tire of the car. So we have the work done by the friction equal to the change of the kinetic energy. The work done by the friction will always negative because the motion of the car on the opposite direction to the friction is always like this. So we have the work done by the friction is equal to the minus Fd, which is equal to the minus 0 minus 1/2 of the kinetic energy. This is the final kinetic energy, which is equal to 0 since the car stopped, and this is the initial kinetic energy. This is for the first part. And if we increase the initial speed to 2v and assume that the car move with the distance capital D before stop, so we have this relation for the second part. Okay, and from this, if we rearrange this equation, put these two out of the square, so we have 4 here, and notice that half of mv square is equal to the Fd. Okay, so compare this to the left side of the equation. We have d is equal capital D is equal to 4d. So it means that the car will move 4 times if we double the initial speed. Okay, so that is for the question number 4. Question number 5. A 3 kilogram cart slides down a ramp. A ramp is 1 meter in length and inclined at an angle of 30 degrees. Okay, the cart starts from rest at the top, experience a constant friction force of magnitude of 5 Newton, and continues to move a short distance on the horizontal floor after it leaves the ramp. Use energy methods to determine the speed of the cart at the bottom of the ramp. Again, we can use the work energy theorem. Okay, when the cart moves down the ramp, okay, it gains the energy from the work done by the gravity. Okay, but also it loses the energy from the friction. The total work on the cart must be equal to the change of the kinetic energy, and initial kinetic energy is equal to 0, and the final kinetic energy is equal to the half of mv square. So we have that the work done by the gravity, which equal to the mgh, is notice that this mgh is equal to the change, the minus of the change of the gravitational energy. So you can see that the gravitational energy reduced by the amount of mgh, and this become the work done by the gravity. And the work done by the friction is minus FL. Okay, as always, the work done by the friction is negative. So if we add these two terms, it's equal to the half of the mv square. But from this triangle, you can see that we have that the height h is related to the length of the lamp by h is equal to L sine theta. So if we put h equal to L sine theta here, okay, we get this relation. And rearrange this relation, we have v is equal to the square root of this term. And if we put the numerical value inside this term, this relation, we get that v is equal to the 2.54 meter per second. So we have the solution of this problem. Now, the last one. How far does the craft slide on the horizontal floor if it continues to experience a friction force from of magnitude 5 Newton? Okay. After the craft hit the floor, it may move a little bit more after it stops due to the friction. Now we don't have the work done by the gravity because it moves in the horizontal plane. So the work done by the object now is due to the friction only. And if it moves with the distance x before stop, we have that the work done by the friction is minus Fx. The final kinetic energy is 0. The initial kinetic energy is half of mv squared. So we have this relation from the work energy theorem. And rearrange for x, we have this. And if we put the numerical value, we have x equal to the 1.84 meter. Okay, so that is for the question number 6.